So now moving on to Trustsec. And this is really the biggest, probably the newest feature in the Nexus platform of switches, and really something that is coming to a lot of the different switches as Cisco continues to roll out new hardware and software architectures for the Catalyst line as well, and routers. And the idea of Trustsec, first of all, we have to kind of define what Trustsec is. So what is Trustsec? Well, it can be a little bit confusing. And the reason that it can be a little bit confusing is that originally when Cisco debuted Trustsec, it really meant 802.1ae MACsec. And that's something that we're going to unpack a little bit more. We're certainly going to go into the configuration of it in the Nexus 7K, and we're going to show what that is. But this is basically layer 2 encryption. However, Cisco decided to basically reuse the term Trustsec, and now it is the next generation, dare I say it, I will, NAC architecture. So actually when they redefined Trustsec to be the overall encompassing architecture for their new next generation security really initiative in the data center and all the way out to every host, and really this is the new bring your own device initiative, is Trustsec. So they decided to reuse that old name. It sounded pretty good. It was actually a fairly new name even when they decided to reuse it in the last few years. But what does this mean for the CCIE data center lab, specifically the Nexus switching portion? Well, as we began to discuss yesterday with AAA and authentication, it could mean that Cisco has an ACS 5.x, probably 5.2, or more likely 5.3 server in the exam, or possibly an ICE server, the Identity Services Engine. But because they don't list it on the hardware and software, not really blueprint. The blueprint goes over the topics, but the hardware and software equipment versions page, it tends to lead you to believe or understand that it probably won't be in the lab, but if it is, then you won't be responsible for configuring that particular device. It would have to be configured for you, and then they would just basically provide you with a preset, predefined list of what what the IP address obviously of that box is, what any shared keys for radius are, because the ICE server only speaks radius, the ACS does still do TACACS, and the Nexus does TACACS, albeit kind of a limited version of TACACS, really the same version, but a limited subset of features, I guess I should say. But it's really a box built for radius. Cisco's future security initiative is based around radius, as is the industry. TACACS is more and always has been the proprietary solution of Cisco, but the Trustsec, what we're believing that it will probably mean is most likely probably dealing with the 802.1ae MACsec. We're going to show you turning on .1x, turning on CTS, the Cisco Trustsec in the 7K, and actually even dealing with some of the other pieces of Trustsec, such as first of all, the SGTs, the security group tags, and the SGACLs or SCAGLs, and even SXP, which is the security group connection protocol, or extension protocol, if you want to call it that. Really, the SXP is the ability to, well, I'll define security groups a little bit more, and then I'll define what SXP is. So let's take a look at what is MACsec to begin with. So first of all, MACsec 802.1ae. Some people call this WEP. All right. So remember that WEP stood for Wired Equivalency Protocol, but it was more like Worthless Equivalency Protocol because it was easily hacked and it didn't really do much. But it got a bad name. If you think about its purpose and what it was there for, and really what we have today. Even though we don't use WEP, we use WPA, most likely WPA2. The idea is that from the beginning, we had this concept that wireless was going to be so insecure, we never wanted to leave it open, that and certainly this is the default in every home consumer device that you buy for wireless, much less an enterprise device. All of my wireless data is encrypted. My entire data stream, not just control with the access point. So my entire data stream is encrypted for wireless. But wired traditionally has not done this. Okay, we could add layer 3 encryption with IPsec or get VPN, all the different flavors of VPN that we could do. But if I just had an Ethernet segment, I didn't typically or traditionally have encryption, certainly not without a layer 3 type encryption. I didn't have a layer 2 encryption. But now it does. Now this is still limited to the hardware, and as I mentioned, Cisco's newer hardware and software architectures that are coming out are going to have and do have more and more support for this. But the idea is that we are actually doing a link by link or layer 2 by Ethernet to Ethernet encryption. So we're actually encrypting before the Ethernet header is written. So, and now this is only supported even in the Nexus 7K on certain types of hardware. So it's not supported on the F series cards, really the newer next generation cards. At least it's not supported on the F1. I don't have an F2 card to try it out on it, but it's not. It is supported on the M1 series card. And I was going to get a packet capture of this, but we have 10 gig E only interfaces, and our tap was a 1 gig E. So we were able to do that for the F series because we could hard code those down to 1 gig in order to grab the fabric path frames, but we weren't able to do this, unfortunately, for the MACsec frames. So really, MACsec is WEP. It's the wireless equivalency protocol, kind of in reverse, right? Now what we're basically saying is that our traffic, just like wireless, can be encrypted link by link at a layer 2 Ethernet level using AES encryption. Now this is not encrypted on the backplane of the switch. This is not encrypted on the backplane of the switch. So really, it's only encrypted as the frame leaves the switch. It's really the final operation as the frame leaves the switch. It's encrypted and then sent out on the link. And then it's decrypted as the frame enters the next switch. So where might this be useful? Well, one of the things that we might want to do is, let's say we were kind of going back to and revisiting what Brian talked about yesterday with OTV and really just DCI in general, data center interconnects. As I have, it's nice maybe that if I have the core of my network and I've got M1 cards or supported hardware cards to be able to have link layer encryption, but in the same way that we didn't have a 10 gig E tap to be able to grab a M1 card, kind of intercept right here in between two switches, it's somewhat unlikely. Although, as time goes on, obviously this will be more and more so available, but it's somewhat unlikely that someone's probably going to walk into my data center and tap into a 10 gig, much less a 40 gig E or 100 gig E port and actually capture the traffic and, try to do something bad with that. Either just capture it for their purposes or intercept it, do some sort of man in the middle, whatever the case may be. But where this really actually does come into play and make sense is in the data center interconnect. Now, the type of data center interconnect mechanism that you use really matters to determine whether you actually can use this or not. And really it comes down to, do I have layer 2 Ethernet or at least simulated Ethernet? So what do I mean by that? Well, if we were doing VPLS, where I have pseudo wires, the XConnect command, L2TPv3, if I'm using pseudo wires, then this really are pseudo Ethernet wires. So I'm encapsulating everything that's coming out of a particular port into a layer 2 encapsulation. So if I've already encrypted that into Ethernet, and then I'm encapsulating that entire payload into layer 3 between data centers, then I can, at the point of egress, I can encrypt that into a layer 2 MACsec 802.1 AE header, and then I can put that into the next device, which is actually going to encapsulate that into my pseudo wire, into my L2TPv3 packet. So MACsec really does work with VPLS. It also can work if I'm doing back-to-back VPC. So if I have dark fiber, and I'm doing this back-to-back VPC between peers at data centers, then I can, as it's going out in Ethernet, encrypt this here on either side and decrypt it on the other side. So I can use MACsec, CTS encryption, what was originally all of CTS, Cisco Trustsec, MACsec. I can use this with really back-to-back VPC or active-active. I can also use it with VPLS. What I cannot do is use MACsec today with OTV, because OTV is really an overlay. It's really not encapsulating that entire layer 2 header or frame or data payload. It is actually just extending that VLAN over top of either my multicast or unicast layer 3 infrastructure. So OTV would have to be encapsulated in some other way. Now, actually, I suppose if I owned the dark fiber there and I was extending OTV over my own Ethernet, then I could do that. That would be certainly fine, as long as I actually have control over that Ethernet header itself. Then, and I'm not taking that layer 2 information and putting it in something else, but I'm actually encapsulating the entire layer 2 frame, then I can run 802.1 AE MACsec. So looking on to the rest of Trustsec, what really Trustsec means today, Trustsec today is really part of what NAC has always been. So beginning with .1x, EAP over LAN authentication, where the only thing that I allow in a given switch port, and again, we're not going to go into all, or really, other than a high-level overview of what Trustsec can mean today, we're not going to go into the full configuration or even really look too far into, if at all, profiling or posturing or anything else, .1x authentication in the ICE environment. But one thing to note, if you are deciding or considering rolling out any sort of NAC or really Trustsec architecture or security architecture, keep in mind that you can do everything in monitor mode to begin with. That is basically turn it on everywhere, but basically don't turn on any of the consequences of it, so that you can gather all sorts of logs and statistical information as to what would have happened if you actually had it in a protect type mode, and then see how this is going to play out in your environment, see how it's going to play against your security policy, if it's going to fall in line with it, if what problems it may cause, but just from a theoretical standpoint, the logs capturing what it would have done right, hopefully most of it, or wrong, and then you can move to an actual partial or fully implemented protected solution. Okay, so when you're considering doing that, take that into account, and it's always a good idea to roll it out in monitor mode to begin with. But anyway, going back, we have this .1x authentication. So really the only thing that's allowed in the port is the EAP over LAN header, okay? And this is something that, of course, we can do on wireless and wired. We allow that EAP over LAN, we authenticate the person, we profile them, we get their posture, we possibly authorize them for the device or resource that they are trying to gain access to. If they don't meet all of our requirements, maybe they don't have the proper level of patches on their operating system, or they don't meet a minimum level of iOS, not Cisco iOS, but Apple iOS operating system level, then we send them to some form of remediation or some sort of sandboxed area. We provide maybe guest services for visiting people, visiting contractors, or visiting just well, guests in our environment. And then Trustsec now includes something called secure group access. And we do this primarily with the Identity Services Engine, the ICE server. We can use ACS 5.3 to provide some levels of Trustsec capability. ICE is certainly preferred, and it is certainly a much more robust and complete solution. So, finally, what is Secure Group Access, or SGA? Secure Group Access is based on two main entities, being the Secure Group Tag, or SGT, and the Secure Group ACL, or SCAGL. So this is a completely new architecture for access control list, really just for access control and access control entries. What this does, and I'm going to go over it in the topology behind me, how this might be implemented or at what points it might be implemented and how it might affect your overall network. But this does actually allow me to, you'll see, significantly reduce the size of the TCAM and memory that I need to store these access control entries. This is based on an egress ACL architecture versus traditional ingress architecture. So let's take a look at the board behind. So traditionally, and even what we were just looking at very briefly in terms of access lists before, I might classify traffic as it's coming into my network. If it's coming in maybe from a server, certainly going out to servers, but maybe in from an access level. So maybe I have some sort of an access level coming into my data center, and maybe at the ingress of my data center, maybe back here at the access level itself, I'm going to be writing ACLs. But the idea, and those are going to have multiple ACEs, but the idea is that I'm classifying at the ingress of my network. Now the problem with this is that I have to write an ACL with access control entries for everything that might live behind my network. So I have to, at this ingress point, I have to take into consideration all the servers that live down here. And let's say we have another FEX down here, and another FEX down here, and another FEX down here. And I also then have to write my ACLs over here because this is another ingress point. So I have to write, my ACLs for all hosts that might live down here or out here or vice versa. So I have to create these extremely complex, extremely robust and long list of access control entries or ACEs within the ACL at every ingress point where I might have a host that lives behind it. And I probably have more than just 2 ingress points to my data center. So as you can understand and imagine, this gets very, it gets overwhelming. Not only cumbersome to the administrator, and really this is something where companies, especially large enterprises, tend to have teams of people that just deal with these access control entry allow. First of all, they get the request. It had to have gone, obviously, through the proper levels of authorization from different management levels, different, has to validate against different data center or security group policies in general for the enterprise. And then someone has to go and manually update these ACLs. And this obviously is going to deal with and at some point begin to overwhelm the TCAM and the memory that's used on these ingress switches. Not to mention it takes a lot of people to administer this in a large environment. So what if instead of just writing an ACL at the ingress for everything that might live behind that interface, what if we basically said, as a host comes onto a network, as my laptop or iOS device comes onto a network, I begin to classify that device as soon as it comes on. I classify it at the ingress. And what I do is I just give it a tag, a very, very simple tag, just a number. I give it a tag. Now, of course, from the human side of perspective, looking at the management architecture, the ICE, the Identity Services Engine, that tag is going to have a more meaningful associated name to it as well. But from the switch's perspective, all it cares about is that tag, the number. Okay? And we can do it in decimal, but obviously the switches are going to be looking at this in hex. So ultimately, that's the format that we'll be looking at the SGT, the secure group tag, in. So we're going to classify all the devices based on everything else, based on their .1x authentication, based on their profiling, their posturing, remediation that they went through. But whatever the ICE server ultimately determines, we're going to give them a tag. We're also going to tag all of our resources that people are trying to gain access to. So maybe I have, I've got my multiple UCS Blade servers here, and of course on those Blade servers I've got multiple VM hosts. And I've got all these virtual hosts over here, got a few full-length Blades, whatever, but I've got all these VM hosts, or I've got all these, standard rack mount servers, whatever it is that the clients are trying to gain access to. I've got these resources they're trying to gain access to, and I give them tags as well. I probably place them into groups. So maybe I've got some sales servers, I've got some HR servers, I've got some IT servers, and it's, I'm oversimplifying things, obviously, but I'm going to group these servers or resources, and I'm going to give them a simple tag value. Now, the idea is that when the ingress device, the host, goes to try to access any one of these resources, a simple comparison is made. So I've got a matrix, and I'm going to actually show this matrix. It comes in a very nice table format in the ICE server. But in the ICE server, I've got a very simple SGT and SGT. So I've got, let's say, SGT 1, 2, 3, and 1, 2, 3, 4, 5, etc. And basically, when the inbound host, let's say, was classified at SGT tag 5, and the egress resource is SGT tag 3, then what I'm going to do is I'm going to basically take a cross matrix and say, what is the cell that intersects the inbound of 5 to the egress of 3? And I'm going to look up what is the SCAGL, the security group ACL. And I'm going to apply that security group ACL at the, and this is the architecturally changing, really fundamental difference of Trustsec and of secure group access. I'm going to apply this at the egress device. Now, really, this N2K, this FEX, is really nothing more than a line card off of either the 5K or the 7K. So it's actually being applied at the 5K's, control plane, but it's logically at this egress port, okay, at this egress FEX. But I'm applying this security group ACL here at this egress. Now, this seems kind of a little bit strange. Like, are we really going to want to allow, in fact, that's what my next slide says, so before any questions are asked, doesn't this mean that traffic that I might not ultimately want on my network traverses my whole network before we drop it? That is what it means. But if you think about it, in the case of a TCP type flow, well, I shouldn't use the word flow. Flow kind of denotes two ways. In the case of a TCP SYN packet, this packet is going to be a single packet that's going to get there before it is dropped in the bit bucket. That kind of points to the SGT map. But it's going to be dropped in this bit bucket. Oops. Okay? If it wasn't allowed. So there won't ever be a SYN ACK that's going to get back and then the ACK to form the three-way handshake. So there's really going to be exactly one packet in the case of TCP that's going to get all the way to the egress point before it's ultimately dropped. So this isn't in any way, at least in the case of TCP, going to overwhelm any of your network resources. It's certainly not going to overwhelm your 10, 40, 100 gig or even larger port channeled interfaces here in your data center. Okay? In the case of UDP, there are going to be a few additional packets, obviously, that get there, but ultimately the application is going to realize that it's not receiving what it was, or it's not going to be responsive, and so it's not going to continue to do what it was, looking to do, and the packets will be ultimately dropped. So it really doesn't present a security concern, and it also doesn't present in any way a traffic concern for the network. But it really is a fundamental rethinking of the way that access control lists are written and used and applied. Now, in terms of TCAM, what does this mean? This is a significant reduction, not only in the amount of overhead and administrative overhead, personnel need that I need. In fact, I've heard reports of groups of 18 security people that were just dedicated to updating access control lists across a multinational enterprise, obviously a very, very large enterprise, go down to a group of like 5 people. So yeah, I suppose that's some jobs, but reallocate those resources elsewhere. I'm not advocating that anyone loses their job, but I am advocating from a business perspective, it makes a lot more sense for large enterprises to not have to have all of these people just dedicated to updating access control lists. At any rate, the TCAM, getting back to the memory architecture of the switch, I now only have to write, and really dynamically, as that access is requested from the end client or the end host, I now only have to write specific access control entries for the SCAGL, the security group ACL, at that egress device. So from the originating device to the egress device, and I actually don't even specify, well, or it's dynamically expanded, I don't even necessarily have to specify, as we'll see in the configuration in the ICE server, source or destination IP address, or even, really IP addresses for networks or for individual hosts for either the source or the destination. So really all I'm saying is that the security group 5 trying to go to the security group 3 is basically blocked from the type of traffic of, let's say port 339 or some other port, 22, SSH or something like that. And maybe I'm allowing, if they had tried to access that particular port at port 80 and they were supposed to have web access, then they get it. Somebody else comes into the network and they're classified as a 4, and from 4 ingress to 3, I take a look at that matrix and it's got a different SGACL. And that different SGACL denies access to even port 80. So because they were coming from a security group that should not have web access to that particular server, they aren't even allowed to connect to port 80. Whereas the devices coming from security group 5 were allowed to maybe have access to that particular egress SGT at port 80. So it's, as I mentioned, a fundamental change in the way that we think about access control entry. Okay, so as I mentioned, yes, the packet does, or the frame does travel over your network before being dropped. Hey, I guess everything does have its trade-offs, right? This is a significant reduction in personnel overhead, in TCAM memory overhead, but the trade-off is that the packet is going to go across your network before being dropped. For TCP, this means exactly one packet, as I mentioned. For UDP, it can mean more, but it's still very effective. This is Cisco's new data center security model. Trustsec is really the new BYOD initiative, and it's very effective, it's very scalable. So we actually already went ahead and looked at some examples, well, at least the traffic flows. We're going to look at the command line here in just a moment. One other thing before we go out and actually look at that command line and example is the NDAC. Well, one other terminology, I guess, bit we should be familiar with, and this is NDAC, the Network Device Admission Control. So the idea is that I have authenticated and authorized network devices. And one of the things that we'll see is that we're only going to honor SGTs, or security group tags, from trusted peers. So in order for Trustsec to actually work, we do really need hardware and software that supports this new model of SGT and SGACL. Now, the SGACL is going to be very similar to what we are already possibly or probably familiar with, known as DACLs, downloadable ACLs. So if I was to gain access to a particular resource, whether that was maybe VPNing in through a DVTI interface, a dynamic virtual tunnel interface for IPsec or SSL or something like that, I might have a downloadable ACL from an ACS server that was automatically applied to my profile and gave me limited resources or limited access to resources then and there. This is very similar. The SCAGL, the security group ACL, is very similar in that fashion, in that it's dynamically downloaded at the time of resource access, when I actually try to access that resource. But the hardware has to know about SGTs. It has to be able to understand and decipher these security group tags. So let's go back to the board. So before I can actually begin setting up security group ACLs, or security group tags really, I have to, first of all, I have to have an ACS server, or actually an ICE server. So we're going to use the idea of an ICE server. Now this server, I'm going to go ahead and erase this. It doesn't necessarily have to be out in the management plane. It may be, but let's just say, going back to the example of I've got a bunch of virtualized servers here in my UCS environment, that I have a VM and it's running ICE. Okay. So my Radius server is my AS, my authentication server. I'm going to have at the minimum at least one what's known as a, and this is fairly common to the .1x architecture, but I've got my authenticator, my authenticator. So my authenticator, or AT, is in the security group tag and Trustsec architecture. This is what's going to be known as my seed device. And I'm going to have at least one seed device. So the seed device will talk to the Radius server, to the ICE server over the Radius protocol. And it's going to, there we go. It's going to first authenticate itself. It's going to be using something that we may be familiar with in EAP-Fast, if we've ever done anything with wireless in EAP-Fast. Cisco's replacement for Leap, really, and answer to the to fast-based security in wireless. It's going to be using something called PAC, or Protected Access Credentials. This is very similar to the way that certificates are handed out with an SSL-based exchange on the web, and we're trying to basically form a quick and secure way of all the rest of our communications. So the ICE server, the Radius server, is over that Radius protocol going to hand down a PAC to that seed device, and the seed device is then going to act as a .1x authenticator for the next non-seed device. Now, the The next non-seed, and this is a Cisco hardware device like a Nexus 7K, for instance, it is going to need to be defined in the Radius server, in the authentication server, but it's not going to communicate over the Radius protocol. So just like if I had an end host, whether it be a server or it be a client of some sort, whether it be an Apple iOS device, whether it be an Android, whether it be a laptop, Mac, Windows, Linux, and it's got some form of .1x supplicant, now we have the switch architecture also as a .1x supplicant. So this .1x supplicant is going to, over its Ethernet link, really try to authenticate to the authenticator using Radius back to the ICE, to the Radius AS server, is going to try to authenticate that device. And now, assuming that the ICE server knows about that non-seed device, it becomes a trusted source. And I drew the other arrow a little bit too soon, but now it becomes a two-way street. It's a trusted source. So any SGTs that come down from this non-seed but now trusted source are going to be honored by each device. And this is what I'm going to have. And I'm probably going to have a few seed devices. It's probably going to be fairly common for a backup and resilience or redundancy type architecture in case one goes down and I need to add more devices later. But as soon as I have either other supplicant, and that green isn't showing up too well over there, if I have other supplicant or they become seed but non-seed devices come on the network, they're all going to, over direct links, if they don't have direct links, then I need to put up another seed server or something else we'll talk about in a moment. But they're going to .1x authenticate through the authenticator. The authenticator is going to look back to the ICE authentication server, make sure that they have a network device listed, see what part of network device group they're a part of, and there's actually going to be an SGT, a security group tag, issued to those network devices as well. So the network devices themselves get SGTs. Now, what happens if we have a device that is not SGT capable, or I should say is not .1x capable today? Well, Cisco thought of that as well, and so basically as hardware is becoming, software is getting upgraded or hardware is becoming more capable, and going along in the progression of newer hardware coming out or just newer software on the hardware supporting this SGT, SGACL, secure group access functionality. Until then, what we can do is we can use a protocol called SXP. So SXP is basically the secure group connection protocol or secure group extension protocol, if you want to label it that. And so we'll use the example today of an N5K that we want to allow SGTs that are coming into this 5K to be trusted by the next device down the line, like this 7K11. So what we'll do is we'll form an SXP, and this is a routed, so it doesn't have to be a direct layer 2 link between the two, but we'll form an SXP connection between an SGT capable device and a non-SGT capable device, and we'll use the N5K as the example for that. So we'll basically form that SXP connection back from both of these 5Ks to one, probably to the seed router would make the most sense, and then SGTs that come into them from something like a supplicant out on another server or on a host, an end client host, will begin being able to be classified through .1x and then ultimately have the SGT assigned the security group tag, and then the SCAGL written to that egress resource that is being requested. So how are we going to do the actual client SGT association or really authentication, find out? That's the purpose of the Cisco AnyConnect 3.0 client. Okay, so the Cisco AnyConnect, again, here's Cisco reusing terminology just to try not to confuse you anymore. But really, AnyConnect used to be used primarily for mobile, right? So being able to do SSL VPN. So now AnyConnect is an entire .1x supplicant that is used for wireless and wired, and it works on Windows, Mac, and Linux, and it not only has just that ability, but it really has a lot of additional features that was rolled in through the security group client, what was it, the security group client, I believe it was the SGGA. Anyhow, that other little bit older client architecture was rolled into, I can't think of the name right off the top of my head, was rolled into AnyConnect 3.0, and some of the things that came with it are the DART, the basically tool for recording all of the errors and anything that might have gone on behind the scenes in terms of authentication gone awry, .1x authentication didn't work right. We now not only have a lot more visibility from the server side, the ICE server, but we also have a lot more visibility from the client side as well, where we didn't in the past. And then there is also something called the NAM, the NAM, or Network Application Manager, that basically we can use, again, Cisco reusing acronyms. The NAM used to be the Network Analysis Module, but now it is the manager that provisions all of our AnyConnect clients, and we create these profiles, and then we can ship those profiles out to our AnyConnect clients, deploy those through whatever architecture we might want, whether that be Microsoft group policy objects or whatever we might want to use to deploy the software and deploy the proper profiles so that they have .1x for preferentially wireless and wired. And so these security group tags begin to be written as devices come onto the network and are profiled, are postured, possibly go through remediation, and then they get the appropriate SGT on the ingress. They traverse the network, they go to the egress device, the comparison of the ingress SGT to the egress SGT is made, that matrix cell is found, and the SCAGL for that particular host to server dynamic resource request is then either allowed or denied. The SCAGL is written down to the egress hardware and into ASICs dynamically and then allowed or denied. So that's the new architecture. We're not going to go into the AnyConnect client. We're not going to go into posturing and profiling. And this is what I was saying. I will be doing some additional videos later that really will go into this entire Trustsec architecture because it's very exciting, scalable, not only a brand new way to think, but it's really quite a brilliant, in my opinion, brilliant way that Cisco has revisited or really re-looked at security altogether in the entire enterprise, not just in the data center. What we will look at today is configuring SGTs and actually radius authentication. We'll go back to one of our 7Ks. We will take the 7K, create it, delete the radius configuration, and then we will put it back, but this time with the protected access credential. We'll tell the ICE server to create that pack to begin with. Using a self-signed certificate, we would probably want to have trusted certificates from VeriSign or GoDaddy or some sort of authoritative source. Ultimately, in a real production environment, this being a lab environment, we'll just use the self-signed certificate of ICE. We will allow this seed device to become fully authenticated. We'll take a look and see what CTS or Cisco Trustsec information and protected access credential was written down to the hardware. Then we'll actually go ahead and add another device. This device will be a non-seed device. We'll define it in ICE. We will not define a radius link from that device back to the ICE server. We will not define that radius link. It will not speak radius from that 7K, and I actually believe we'll be using 2K5 and 2K7 are the two that we're actually going to be using in our topology today. But it won't speak radius back to the server. Instead, it will speak .1x over to that seed device, and our diagram's getting a little messy. So this was the seed device down to the ICE server. It will be .1x authenticating over from the second 7K to the seed device, which is the authenticator. The authenticator will speak radius down to the ICE server. The ICE server will reply radius to the authenticator. The authenticator will reply back to the non-seed device and will authenticate it, effectively making it a now green trusted in terms of security group tags and security group access. We will set up MACsec on this link, so we'll actually take a look at the encryption, the AES encryption here, and take a look at also the ability, can we do MACsec without security group access, without SGTs, without the ICE server? Yes, we can. We can set up just manual encryption link to link if we don't have or haven't rolled out this entire architecture yet. And again, just the manual turning on of that MACsec is what Cisco traditionally called CTS, Cisco Trustsec. It is what I would think you'll probably have more. I would actually go so far as to say I can almost guarantee when Cisco lists on the blueprint Trustsec for the CCIE Nexus portion, you'll definitely have layer 2 link encryption at a manual format. Whether you'll have it with .1x, kind of an automatic format because of the whole Trustsec architecture, again, depends on whether they have the ICE server. But if they do, you won't be responsible for, can't be held responsible for provisioning the ICE server because they didn't list it on the hardware software. Could they come back at a later time with a blueprint reversion and add that? Of course they could, but that would be for a later time. And if they did, they would just have to provide you with the information, you know, what is that device, IP address, what device is the ICE server expecting that IP address to register on, so what layer 3 SVI or management interface do I need to use, and then also what is the trusted shared key. And it really wouldn't be that big of a deal if they did that.